All right. Thank you very much to everybody for coming out, and we'll get you to coffee break as quickly as possible. I'm going to use the next 15 minutes, not quite lunch yet. I wished it was lunch, but not quite there. I'm going to use the next 15 minutes or so to talk a little bit about the effect of atmosphere-ocean oscillations on the nature of avalanche hazard in Western Canada. This is actually research that Brett Chandro, one of my master's students who graduated last fall, conducted. At this point, I also want to sort of acknowledge Patrick Meyer, who helped us out with the statistics on this research. Now, every fall, this community here in particular gets in a bit of a frenzy about whether we're going to have a La Nina or a La Nina year, or whether El Nino is back. And every time we're sort of wondering what are the snow gods going to do and how is that going to affect our ability to shred powder. And I've even seen real estate agent in Whistler advertising with the fact that La Nina was coming to Whistler and that it would be a fantastic winter for shredding some POW. Now, the effect of La Nina and El Nino on winter weather is actually fairly well understood, and I'm not really the right expert here to talk about this. There's people like Matt McDonald, Trevor Smith, and David Jones here in the audience who are much better at explaining what the effects actually are. But I can give you sort of the big overview, and if I speak off my notes here, then please David and Trevor just speak up. But generally, during the El Nino winter, as we all know, we generally have a warmer than average pattern over Western Canada, actually most of Canada. And during a La Nina winter, we generally have colder than normal temperatures, and there is even a slight increase in precipitation pattern. And that's generally when we get these really good winters for our skiing. Now at the bottom you see sort of what kind of patterns we had over the last couple of years. So the last big El Nino winter was 2016, which was that winter that was significantly warmer than normal, that posed a little bit of a challenge for the skiing community. And then 2011, we had the last strong La Nina winter, and even the last winter was sort of a slight La Nina winter. So this is probably nothing new to this community, where all of us are pretty much well aware of these patterns. Now, ENSO, or El Nino Southern Oscillation, is not the only atmosphere-ocean oscillation that actually affects the winter weather patterns in Western Canada. We also have the Pacific Decadal Oscillation that also has positive and negative phases, which is primarily related to sea surface temperatures in the northern Pacific. Here, the positive phases are generally associated with warmer temperatures in Western Canada, the negative phases with colder temperature, and it generally just has sort of a modulating effect, so a strengthening effect of the ENSO pattern. We also have the Pacific North American pattern, which is more of a pressure pattern in sort of the middle of the atmosphere, which affects where storms are going and where the jet stream is. And that as well is heavily linked to the ENSO pattern. So there's a big correlation between those three atmospheric patterns that are sort of focused around the Pacific. On top of that, we have also something that's called the Arctic Oscillation, which relates to the pressure gradient, so the difference in pressure between sort of the polar regions and the mid-latitudes. And here, a positive phase is related to a stronger pressure gradient, which results in a stronger jet stream and generally a more zonal flow, so a directly sort of west-easterly flow, in comparison to the negative phase, where we have a weaker pressure gradient and therefore a more sort of undulating jet stream. So all these things together sort of affect the weather patterns in Western Canada. And their strength are generally sort of measured with a couple of indices. And there are a bunch of them around there. For the ENSO pattern, we have the MEI, which is shown here in the red curve. So this is sort of these indices are provided on a monthly basis, and what we've done here is we basically downloaded those monthly values and then averaged them out over the main winter months, so from November all the way to April. And so you can see here with the red curve that represents sort of the intensity of the El Nino that we had, sort of the La Nina winter in 2011 and the El Nino winter in 2016. What you can see on this graph already is that the PNA and the PDO are strongly actually correlated to the ENSO, so they sort of follow the same pattern with more negative values earlier and then more positive values towards the end. The purple curve here is the Arctic oscillation, and you can see that that sort of varies on a different pattern. So given that these oscillations have a very strong effect on the winter weather in Western Canada, it's not really a stretch to think that they also affect the avalanche conditions in Western Canada. And the first person who actually looked at this, and they didn't explicitly link it to these oscillations, was Fitzharris in the late 1980s. And he was sort of the first to consider these sort of large-scale circulation pattern and trying to link it to avalanche activity in Rogers Pass. And he used sort of the long-term records that CP had about avalanche activities affecting their railway line. More recently, Dave McClung in 2013 looked at the relationship between ENSO and avalanche activity at Bear Pass and Kootenay Pass, and his results were that La Nina generally result in more snow, more avalanches, and a higher percentage of dry avalanches. In comparison, El Nino would result in less snow, fewer avalanches, and a lower percentage, or a higher percentage of wet avalanches, which makes sense related to the warmer temperatures in general. Scott Thumler, Bruce Jameson, and Sasha Belair in 2014 in an ISSW paper also looked at that kind of stuff, but they used records from 6 highway passes, and they basically confirmed the results. Or Dave's results. And they also found sort of a similar relationship with the Pacific Decadal Oscillation. In addition to that, they actually found a correlation with the North Atlantic Oscillation, which is another one of those patterns, but more centered around the North Atlantic. And here they found that a positive phase there was associated with an increase in wet avalanche activities. Now, all of these studies provide quite some interesting first insights about how these oscillations affect the nature of avalanche hazard in Western Canada, but there are a number of shortcomings. One is the observations that you use are focused on very specific point locations in Western Canada. It's basically tightly monitored highway corridors where avalanches have been recorded for a long time. So they can't really provide a global perspective on how avalanche hazard is affected. The other aspect is that avalanches occurrences by themselves don't really give a good picture or a comprehensive picture of what the hazard conditions were for a whole winter. For example, you could be dealing with a deep persistent slab for the whole winter that really dominates how people behave and how they manage the risk, but you actually only have very few avalanches, very big avalanches potentially on that weakness that wouldn't really show up that much in these records. And that's where really sort of the idea of our research came from. How can we take another perspective that maybe sheds a little bit more light on these relationships? And this is where the bulletins come in. because the bulletins really provide a much more comprehensive perspective on what the conditions are out there. They are basically an expert assessment of what people should be concerned about and how they should be managing the risk. And since the introduction of the conceptual model of avalanches, of avalanche hazards, this information is actually recorded in a very structured way that has the potential to be analyzed in an analytical way. Now, the challenge is we have lots of bulletins. The conceptual model was introduced in 2010, and since then, every bulletin in Canada basically is built on that foundation. But how do you summarize all that information in a way that we can actually analyze it and potentially correlate it to those indices that I showed you before? The first step to go to is to sort of the hazard chart, which I'm sure everybody in here is familiar to, which gives a very concise picture of the conditions at one time in a sort of quantitative way, because it tells you what kind of avalanche problems were present, what was the range of the likelihoods of avalanches, and what were the expected sizes. The challenge is that when we look at all bulletins, there is a wide variety of possible combinations of these avalanche problems. And the question is, how do we summarize that? And this is really where sort of the focus of Brett's research was. And he used sort of a machine learning clustering algorithm to try to find what are the key patterns in here, what are the most common patterns out of this vast range of different possible combinations. And what he came up with was 13 distinct sort of typical patterns that are out there. And I've listed them here from sort of the most simple patterns at the bottom, where we, for example, had no avalanche problems at all, to the more complex one towards the top. For example, number 8 were situations where we had a storm, a wind slab, and a persistent slab all together at the same time. What you see on the right here are examples of typical hazard plots for those situations. So for example, the one up here relates to the wind slab only situation down here. So this gives you sort of a sense how the hazard chart would have looked during those times when that was sort of the primary case. At the bottom, you see sort of the storm and persistent slab situation where those two problems were present at the same time. Okay, so now we have basically for every day, for every bulletin can be assigned to one of these 13 problems. And what we can do now is calculate how often those problems are actually present. And so what you see on the right is sort of a stacked bar chart that shows you how often these different problems are present. So the no avalanche problem in the whole data set was present about 15% of the time, and so on. The blue colors here indicate avalanche or hazard situations that were dominated by the storm slab situation, and the orange ones up here are situations that were dominated by some persistent problem, just to give you a little bit of a sense. So that what you see, the graph on the right, is basically across all bulletins that we've had for the last 9 seasons. Now, with that, we can now look at patterns. And what you see is sort of spatial patterns. So now you can see this bar chart for each different forecast regions. And you can immediately pick up the Rocky Mountains here, which have a much higher prevalence of the persistent slab problems. You can see that the coast mountains have sort of a more simpler situation. So there's the bars at the bottom are a little bit taller. You can see that the Purcells are quite different from the rest of the Columbia Mountains, and so on. We can also do this over time. And you can already see here that sort of the winter 2009-2010, some of you remember this was the time when we had at times 3 persistent weak layers active at the same time. So you can clearly see that pattern here. And you can see the 2016 winter over here, which was the very warm winter. So you get the sense. We can now sort of look at spatial and temporal patterns. And the immediate thought is, well, can we now correlate this to our climate indices? And so let me just recap the data set that we have for this analysis to now try to sort of look at this relationship. We have the average winter oscillation indices. We have all avalanche bulletins from Avalanche Canada and Parks Canada from 2010 to 2018 for 22 forecast regions, which comes out to be about 15,000 bulletins. That allowed us to basically create these seasonal prevalence values. And to look at this relationship, we used a better mixed effects regression model. We basically tried to create a model for each of these percentages to link them to these climate indices. We only used alpine and tree line hazard assessment, and because all the Pacific oscillations are so highly correlated to each other, we only looked at ENSO and the Arctic oscillation, and we didn't include everything. If you have questions about sort of the details of the mixed effects model, you can ask me about that after the presentation. Okay, so let's look at the effects that came out of this. So everybody is familiar with the forecast regions, and we're just going to look at the avalanche hazard situations that are the most prominent. So we go sort of top down in that list. So we'll first look at just pure wind slap situations, which were responsible for 19% of all the hazard situation. And what we find here is that the Arctic oscillation results in an increase in wind slap hazard situation along the coast and a decrease in the Rocky Mountains in general. ENSO results in a decrease in wind slap situation on the coast, so the sea to sky, and an increase in the northern Columbia Mountains. Let's look at another example. This is the persistent slap plus situation. Those are persistent slaps that are generally on the larger end of the spectrum. On this side, we basically have a decrease in the Rocky Mountains, at least in the northern parts, but an increase in the southern part, and a decrease in the coastal mountains. For ENSO, here the pattern is different. We generally see an increase in that hazard situation in the northern parts and a decrease in the southern part. And so you can already imagine that maybe the storm patterns just slightly shift around from north to south that would result in a change in the patterns like that. Deep persistent slap situations, there's absolutely no effect or no effect that we were able to identify from the Arctic oscillation. And with the ENSO, there was only a very minute effect that we could find sort of in the more southern Rocky Mountains here. Again, sort of the opposite effect between Banff and the South Rockies, and then there's a little bit of an effect in the north up here. And if just one last one here, the storm slap situations here, we see sort of an increase in the storm slaps with the Arctic oscillation in the coast and the Columbia Mountains, and a decrease in the Rocky Mountains, and there's a little bit effect of ENSO. So this is just sort of 5 examples of what kind of patterns we can actually identify with this analysis, and it's about as much as I can remember from the top of my head. Or I guess I thought I could remember one more. So let's just quickly look at sort of the overall effect of the Arctic oscillation. So we have sort of more wind, less persistent slabs there in the Rockies, more storm, and more, now I just lost track, less storm. So that basically gives you a fairly comprehensive overview of what the effect is. On the other side, the El Nino, this picture here gives you an overview of that effect. So it gets pretty complicated to sort of keep all those patterns in your mind right all together. But I think it is a much more detailed perspective of what the potential effects are. Let me finish up here. So what I've tried to do is to relate these atmospheric ocean oscillation indices to the nature of avalanche hazard in Western Canada. I tried to sort of come up with an approach that provides a little bit more of a comprehensive pictures than the studies that we've had before. The results are generally realistic, so it seems to make sense, the patterns, given what we know about the weather impacts that these oscillations have, but it's a really small data set. Like, it's about 8 winters that we have, and so I wouldn't put too much weight into the results, but I think the method is a useful step forward. We were also unable to sort of isolate the individual effects of these specific focused oscillations. That's just the nature of those recent years, and I hope that with a longer data set, we'll eventually be able to tease those out individually. But I think it is sort of a possible approach that might lead us towards the direction where we can potentially have the ability to do some seasonal forecasts for the upcoming winter of what kind of an avalanche winter are we actually dealing with. Now, if you're interested in sort of the details of this, please visit our website. Brett already published the first half of his research, and it's publicly available, so you can download it straight from there. I want to thank our sponsors of our research, and then I would open it up for questions, but I think I'm already over time, and I don't want to hold you back from your coffee break. But if there's any questions, I'm happy to take them. Thank you.